Okay, so question 5, exam 1 review. Again, the question says the RMS speed of a molecule at 20 degrees Celsius is V. The speed of the molecule is 1.5 V at a temperature T. What is that temperature T? And the choices are in degrees as well. So again, it's another, like question 4, it's a question on RMS speeds of a gas, the root mean square speed. So again, thinking about how we define the RMS speed of a gas. So the RMS, and then you can go to the 3 RT version over the molar mass, or the 3 kBt. For this question, it doesn't really matter, or 3 kBt times the mass of a single molecule. So this question is more of a proportional reasoning question, so we don't have to worry too much about the quantitatively, although it is a quantitative question, but just sort of proportionality ideas here. So I'll show you the sort of the way that I would like you to solve the question. So the question is stating sort of the relationship between V, the speed, the RMS speed, and the temperature. So I'm not going to worry it's the same molecule, R's and these KBs are constants, the mass is not going to change. All we're doing is changing the temperature, seeing how the speed changes. So for a given molecule, or a given molecule or a single atom, the RMS speed is proportional to the square root of the absolute temperature. So it's proportional. This is where I said it was a proportional reasoning problem. Sort of scaling, and thinking about how quantities scale with each other. So the RMS speed scales with root of T for constant mass. So if you're just thinking about a single gas molecule. And we're interested in a sense how the temperature changes as a function of V. Now how V changes the function, well, this kind of tells us how V changes the function of temperature, and we're going to want to know, like, how does temperature change as a function of the RMS speed. So we would take the square of both sides of this expression and say that T scales with the RMS speed squared. So if the RMS speed were to double, the absolute temperature would have had to have increased by a factor of 4. The RMS speed increased by a factor of 3. Then the temperature would have had, the absolute temperature would have to have had increased by a factor of 9. So to get changes in RMS speed, this is sort of the relationship you have to consider with the temperature. So we know that the speed increased by a factor of 1.5. So that means that the new temperature would have to be scaled by 1.5 squared of the old temperature. That's how this scaling relationship works. So T new, the new temperature, would have to be 1.5, the factor by which the speed changes, times the old temperature. So that's one of the difficult parts of the question initially, but we're not finished. We're far from finished, because you've got to be careful. There's a bit, here again, anytime you're working with RMS speeds, you must be working with absolute temperature. So it's not 1.5 squared times the 20, but 1.5 squared times the temperature in Kelvin. So the new temperature is going to be 1.5 all to be squared times the original temperature, which is 293 Kelvin. And that gives an answer of 659 Kelvin. But the choices are in degrees. So we have to, so this is, in a sense, this is how much the temperature would have to have changed. So it would have to have risen from 293 to 659 in order to get a factor of 1.5 increase in the RMS speed. So our last step is to figure out what is the temperature in degrees. So we take that 659 Kelvin, and then we subtract the 273, and that gives us 386 degrees Celsius. I went overboard here on the sig figs, but choice C is the correct answer. Yes, again, like question 4, the RMS speed equation just tends to have, I guess, three variables: the speed, the temperature, and the molar mass. But it's really highly emphasizing the importance of units, that the temperature must be in Kelvin, molar mass must be in kilograms per mole, and then you can look at the question in terms of also proportional reasoning, that the RMS speed is proportional to the square root of the temperature. The RMS speed is inversely proportional to the 1 over the square root of the molar mass, or the mass of the molecule. I'll just for additional use, I'll just use this little bit of space over here if you're not completely comfortable with the sort of seeing these scaling relationships. I'll show you why it's important to see these, because how much longer an alternative method. So I'll just use this space here. So you could have started the question by stating that the RMS speed at 293 Kelvin is equal to this V that we're getting, and will be equal to 3 times R times 293 Kelvin divided by the molar mass. Now we know the V at this new temperature, the new, at T prime or T new, we know we have 1.5 times this V RMS at 293. So 1 times the V at the room temp corresponds to 3 times R T new, all divided by the molar mass. Now, since what we have here, we can equate these two things here. So let's say that 1.5 times the square root of 3R times 293 divided by the molar mass equals the square root of 3RT nu divided by the molar mass. And in both equations you have the square root of 3R over the molar mass, and both sides of those will cancel. So we'd end up at 1.5 times 293 Kelvin, the square root of that, equal to the square root of T nu. So to get T nu, you'd have to square both sides. So T nu will be 1.5 squared times 293 Kelvin, which is exactly what we had over here. Now, maybe it's a bit subjective about how long these steps take you, but once you have the proportionality, it can be a very useful technique to see that you don't have to concern yourself with constants if you're just looking at a proportional reasoning question.